All right, so good morning, everyone, and thank you for coming today to our CA seminar series. It is my great pleasure to introduce to you today to Dr. Houman Hadad, who is a senior project engineer at DeSimone Consulting Engineers, and he actually got his PhD right here at So welcome back. Dr. Hadad is a member of DeSimone's Technical Advisory Group. So he conducts research on a variety of topics. My understanding is he's an expert on these structures and wind, South Florida, important topic, but he also does work on resilience and on reducing embodied carbon in structures, which is a topic that he's gonna tell us today about. He's also a member of ACI committees and a chair of the ACI Technical Subcommittee 5. I actually don't know what this committee is. 549-K. So with that, Dr. Hadad, welcome. Thank you for being here, and the floor is yours.
Thank you very much, Luis. Hello, everyone. Nice to meet you. Thank you for coming to this presentation and talk today. So today's talk is going to be about reducing embodied carbon of structures, and mostly because I'm practicing structural design, you're going to probably see it more from the perspective of a practitioner rather than a material person. So what we're going to be talking about is some introduction of the firm and myself. Why do we want to reduce embodied carbon? Some talk a little bit about carbon basics. Where does the embodied carbon come from? How to reduce it, and eventually some market trends and what is going on in the world that we live in right now in the construction. DeSimone Consulting Engineers, we are at the core a structural consultant company. So what we do, we design structures that has been historically the core of the firm, and even today the majority of the work. But we've been expanding into other areas, including structural design, facade consulting, forensic engineering, risk management, and other areas. I'm very glad that at least for people that are in Miami, which I think there is majority of the audience, a lot of buildings that you know by name, including 1000 Museum of Zaha Hadid, Panorama, Paramount, Flatiron, the Twisting Tower of Grove Bay, and many more have been work of our company at the end. So we kind of helped shape the Miami skyline to some point, and I take pride in that. So why do we want to reduce embodied carbon to begin with? If you think about traditional structural design criteria, we are trained to think about safety, and by safety I mean occupant safety, right? Against seismic event or hurricane winds or even the gravity load. If you have a pool up top of the structure, you have to support it. So safety. Then you have cost and schedule and constructability that go hand to hand. A project has to be economically viable to be built, a development, and then it has to be, good to be constructed at the end of the day. And aesthetics goes without saying. No one wants an ugly building. So this is what we traditionally had. If you want to think of sustainability, I don't think sustainability adds here as another item in the traditional design criteria. I think it's a layer on top of all of them because it encompasses safety, cost, schedule, constructability, and it affects each of these items in a way. So when you're thinking about sustainability, right, you don't think about safety of the occupants only. You're thinking as a civil engineer about safety of the community, of the public safety that we are living in, right? It definitely affects the cost, schedule, and constructability aspects of a project when you think about sustainability, and aesthetics as well. So it's another layer on top of everything we have traditionally had. And then sustainability has some more added values. Obviously, we think about and we care about climate and biosphere care, the holistic public safety that I mentioned earlier. As a civil engineer, you not only think about the structure that you're designing and safety of occupants, you're going a step further and you want to protect the public. And obviously it works well with talent acquisition and marketability these days because reality is, and based on all the polls they are doing, our generation, the millennial generation and Gen Z and onwards, they do care about sustainability to a good degree. And then therefore, the companies or projects that can pose themselves as sustainable, they have an advantage when it comes to marketability and it comes to hiring new talent that is entering the job market. And obviously, the graph on the right is showing the building sector is responsible for a good amount of carbon emissions, CO2 emissions. So if you are responsible for a good amount of it, we probably have some levers to pull to reduce it also to a good degree. And then I go to SE 2050 challenge. That is a challenge that is started by Carbon Leadership Forum. If you're not familiar with Carbon Leadership Forum, Google it, go dig a little bit deeper. They have a lot of good information. They have a very good, well set up website, and it's very educational, really. So Carbon Leadership Forum started the SE 2050 challenge. The goal is to go zero embodied carbon by 2050. And then ASCE SEI adopted that challenge. And now there are signatory firms that basically pledged to that challenge. Our firm is one of them. That list has grown ever since that I had the list in my desktop. And it's a lot of more companies are joining the movement, essentially. I want to make a note here that today's topic is going to be about embodied carbon. And embodied carbon, we mean the carbon that has been released by producing the material that goes into your structure. We're not here to talk about operational carbon, although it is very important. But I think as a structural engineer, you have less impact on operational carbon. Operational carbon being the energy you use for cooling, heating, air conditioning, all the electricity that is used in a structure. We are more, I think we have more influence on the embodied carbon, on the material that is used to build a structure, essentially. Now, let's talk about some carbon basics. And I want to talk about 3 different materials that are most common in construction, right? I want to talk about steel, concrete, and wood as 3 different structural systems. First, we go to steel. So to make the steel, crude steel, there are 3 different approaches, right? One is basic oxygen furnace. That is the oldest one. The way you do it, you have the iron ore, or you add coal, coke, limestone, and other stuff to it. And you essentially burn fossil fuels to heat it up and melt it and produce, at the end, you blow some purified oxygen to the mix to manage the level of carbon in the metal that comes out of the furnace, and that's how you have your crude steel. The other more recent technology is DRI, or direct reduced iron. What you do is that you're not burning fossil fuel anymore to heat up. You add stuff, you have direct reduced iron, and eventually you go to recycle the steel. You can add recycled steel, and you go to electric arc furnace, which heats up using electricity. And then there's a third way of making steel, which is just recycling steel. So the steel that has been used, you melt it again in electric arc furnace, and you make new steel out of it, hot rolled shape, right? I'm happy to say that in the United States, most of the steel that we produce, at least the hot rolled shape, are produced with the last process that I explained, or electric arc furnace. And I'm happy because electric arc furnace releases less carbon dioxide compared to other 2 processes, specifically compared to basic oxygen furnace. So that's a good thing. Another thing to remember again is that electric arc furnace consumes electricity to generate heat. So therefore, where your plant is, where your mill is, a steel mill is very crucial here. Are you located in a state that has a clean electricity grid, like the West Coast or Pacific Northwest, or if you can see in this graph here, the Northeast region? The yellower in this graph, the cleaner is the electricity grid system. Or are you the mill happens to be in one of the states that is more carbon intensive, including the Midwest. So that changes a little bit the equation of the steel at the end of the day. Then let's talk some numbers. So for steel, in average, we have 1.16 ton of CO2 released per ton of steel produced. That is a high number. Reality is, so for 1 pound of steel to make, you are making more than 1 pound of carbon dioxide and release it into atmosphere. That is obviously subjective. It depends again on the technology, on the mill, where the mill is located. The number changes. A lower bound is 0.7. That is for a mill in Seattle area in Pacific Northwest. There's a new core that they are using the latest technology of electric arc furnace. And then it can go to higher for older mills that they are still using the basic oxygen furnace, essentially. And then also based on what steel shape you're using, the numbers change. To produce reinforcing steel, the rebars, it's usually produced with electric arc furnace, and it's usually less intensive in terms of shaping it, rolling it. And then you have a number that is close to 0.9. I know that all of the W shapes in the United States are produced with electric arc furnaces. But when you go to cold form steel and a steel deck, it's mostly still produced with the basic oxygen furnaces, and those are more energy intensive. So when you go to steel, depending on what shape you're using in your design and where you're sourcing the steel from, the numbers can change very significantly. From steel, let's switch to concrete now. And we talk a little bit about cement. Again, we're just talking about carbon basics here. We are interested to know where the carbon comes from in every of the single materials that we mentioned. So in concrete, what is the paste? What is the binding agent? That's the cement. And cement, to create the cement, essentially you have to mine the raw material, you have to make the cement from the clinker and cook it, and then you mix it in the ready mixer, you transport it to your job site, and that's how you have concrete. The first two processes here, mining and cement manufacturing, are responsible for 70 to 90% of the embodied carbon of concrete overall. So let's dive a little bit into cement manufacturing. Cement manufacturing starts with raw material. You have to crush it, dry mix it, then you preheat it, and you have to cook it in a kiln, cool it down, store it, crush it, bag it, and then it goes to the customer. So it's a little bit similar to how you cook a steak, really, right? You pre-season it, then you take it out of the fridge so that it gets room temperature, you cook it, you cool it down, and you eat it. For the two processes of preheating and cooking the cement, what is usually used to generate, you have to generate heat for preheating and for cooking, right? It's mostly either fossil fuels, or recently is being more and more common to use gas, nuclear energy, and other source of wind energy and whatnot. So that's one way that you're releasing CO2 in the process. The other way is that by a chemical reaction, calcination in the kiln, when you are cooking the limestone, essentially you are releasing CO2, which is an unwanted byproduct, and you end up with the lime. That also releases CO2 into the atmosphere naturally, and that's sometimes more than the CO2 that you consume just to basically burn or to heat up the kiln and preheating process. So then let's talk about the numbers for cement. So what you're seeing here is called an EPD. EPD is almost like nutrition fact they call it nutrition fact for materials these days of anything that you buy in the store. Like the nutrition facts, you probably are most interested in the number of calories that you're consuming, right? In that case, it becomes global warming potential, or how much carbon dioxide is released into atmosphere as a result of creating 1 pound of that material. So for cement right now, the number is 922 kilograms of CO2 per every ton of cement that is produced. So it's a number close to iron, again, to steel that we saw before. It's a high number, but I'm happy to see this number because 3 years ago, when we were doing some research on sustainability again, the EPD that was released by Cement Association was 1,040. So it has reduced. That is saying that the new technologies are being implemented, 2, the energy grid system is being cleaner every day. And 3, I think it's just that the cement plants are putting effort into reducing their embodied carbon and carbon release into atmosphere. That's for cement. Now from cement, if you want to go to concrete, concrete is basically a blend of cement and other materials, including the aggregates, the water, and other admixtures. So a ready mixer essentially knows exactly how much of what material goes into a concrete. And they have EPDs for every single one of these ingredients, and they can do the math and come up with an EPD for the specific mix of cement that is being released as a batch to a job site. Even better, they report all of that data to NRMCA, which is National Ready Mixer Concrete Association, which is the association that really represents all of the cement manufacturers. So then NRMCA gets all of that data and creates a big, nice database, which is the national average of GDP for global warming potential for cement, essentially, and for concrete around the country. And they do that by they have different classes of a strength for concrete, and they have different cement replacement. So was it up to 20% replacement of fly ash? Was it up to 30%, 40%? Was it more or less? And they associate one average number to every of these essentially categories. And these numbers are very important because eventually any of the LCA softwares that are working right now in the United States, they mostly rely on this data for the average of global warming potential for concrete. And life cycle analysis, or LCA, that I mentioned before, it's very simple process at heart. What it is that you have quantities of materials and you have carbon intensity associated to that material. You multiply these and you do that for every single element or concrete, steel, whatever member that you have in the structure, and you add it all up to see how much at the end of the day, how much carbon are you consuming, right, for that project. So that was for concrete. Now, the third material that I want to talk about is wood, third structural material, which is becoming very fashionable these days, and a lot of people are interested in it. The processing of lumber or wood is that you have harvesting, you have logging of the wood, then you essentially transport it. It goes through process of milling. In the milling, it has to be debarked, rough cut, stacked, and then it's dried, either kiln dry or air dry, depending on the mill. And then essentially it's transited and ready for use in your structure. If you want to talk about numbers of carbon intensity for wood, reality is that a lot of people say that wood is either carbon neutral, zero carbon, or a lot of people argue that wood, because it stores some CO2 during the natural life of tree, they call it sequestration, is actually carbon negative, right? There is some argument there because two things. First, the wood that you're consuming has to come from smart forestry practices. It cannot be a wood that result in deforestation. That's number one, and we're not even talking about carbon emissions yet. Number two is that during the process of logging the wood and also disturbing the soil, some CO2 is released. How much is it? Is definitely much less than what concrete and steel release, but it's not zero, it's some amount. And then essentially there's another argument that at the end life cycle of wood, either it decomposes or it ends up being burned if it's not recycled properly. And either of these two releases the CO2 that wood has been absorbing throughout its life. So there's argument that, all right, we cannot take every single wood that is in the market as carbon negative. It has to be a little bit more scrutinized. It has to be studied a little bit more and see how it is. But the fact at the end of the day remains that wood compared to concrete and steel is not carbon intensive as much as they are. Maybe it's not zero, maybe it's not negative, but it's not definitely 1,000 kilograms of CO2 per a ton of wood produced. So now we talked about 3 different materials and each material, how carbon intensive they can be. From there, I want to talk about some reduction strategies in real world. We have a project, you have a client, you are the structural designer, they come to you, and there's a goal of reducing carbon in this project. There are some general decisions to be made and some material specific decision depending on the structural system to be made. In general decisions, I think the most important is to understand the team dynamic and reasons behind the reduction, right? What is driving this project to reduce embodied carbon, either 10%, 20%, 50%, or go fully carbon neutral. And that depends, that really dictates how the project is going to go. So is that a request from the owner? Does the owner want to reduce it because they are a sustainable person? Are they doing it because they want to achieve a target limit for carbon dioxide because they want to get this certificate? And I'll talk about certificates later on. Or is it coming from the structural designer, us, and the owner is not even aware of it and they don't want to spend a penny on it? Is it coming from the architect? So all of these really changes the dynamic and how you approach a project that wants to reduce carbon. Then the second important decision to be made, I think, is specifying a carbon goal. So what is your goal? Assume that someone wants to reduce carbon in the project or all the parties together. What's the goal? Do you want to go overall carbon neutral, like Apple pledges to do now? Or do you want to reduce to a certain amount per pound of material or per square foot of the structure so you can use it in marketing later on, or you can hit a certain certificate? And different reasons for it. So that carbon goal is very important to set. Third is structural design decisions. And I think this is very important for the talk of today because we are talking to School of Engineering and all of you are going to be engineers at the end of your program. So structural decisions play a big role. I want you to imagine a high-rise building like Panorama here in Miami, right? 85-story building, concrete, and it goes basically PT floors all the way 82 stories. The decision at some point, there will be decisions to be made that what is the span of columns, right? Compared to what is the thickness of your slab. So imagine 82 stories. If you could reduce 1 inch thickness of a slab multiplied by the floor area multiplied by 82 times all the floors, that is a considerate amount of concrete that is reduced. Now, to reduce that 1 inch, you need to sacrifice something. That something usually ends up being that the column spacing, for example, has to be a little bit closer. Sometimes it works, sometimes it doesn't. So the whole team has to be on board. Again, can the interior designer and the architect achieve that goal of 2 columns being a little bit closer, but in turn reducing 1 inch off the slab, right? And getting that vertical spacing as well. Now, if you reduce that 1 inch, not only you're reducing the amount of concrete that is used in the project, but also you are reducing the overall gravity weight. So your columns can now shrink because there is less weight on them. And then at the end, everything in the foundation can shrink, and maybe you need less piles in the foundation because you reduce the gravity load on all of the column piles. So the structural design decisions to be made, I think these are very important and very crucial. Some of the structural design decisions you make will affect essentially the project, the schedule, and the cost. Some of them will have almost zero to none effect. And we'll talk about them a little bit later in material specific. Then you have a study alternative structural system where possible. So here, I don't think this is one size fit all. I told you a second ago that wood is more sustainable or is less carbon intensive compared to steel and to concrete. But it doesn't mean that every project can go or should be made of wood. Again, a project like Panorama, you cannot make that out of wood, right? It has to be either concrete or steel. But some portions or some members of Panorama could be in wood, right? And some smaller projects, a lot of residential housings and condos can be in wood. Essentially, when you have to study alternative structural systems. And I think that is a big decision to be made. Then material sourcing, closer and cleaner is obviously better. This is just you smart shopping. So when you're going to a grocery store, instead of just buying anything that your eye sees, you make some decisions, right? That, hey, I want to buy healthy food to be healthy at the end of the day. And you're doing the same when you're building a structure. I want to specify materials that are sustainable, that are meeting my project requirements, the goals, the carbon goals that I've met at the very beginning of the basically project. And then essentially there is a possibility to use carbon offsets. And this one is very controversial, to use carbon offsets. What are carbon offsets? Carbon offset is that you imagine you are American Airlines. A lot of big companies do that. You, as an American airline, you are burning fuel to take passengers from point A to point B. You want to be sustainable, but you have to burn that fuel to go from point A to point B. What you do instead is that you buy into a project that they plant trees in Amazon, in Brazil, or in Indonesia. And that in turn, that forest that you created will offset some of the carbon that you're consuming today, right? It looks very beautiful at the first glance, but there are nuances. And a lot of people call it greenwashing these days. Depends, right? First thing is that it really depends where you're buying your carbon offset from, right? In case of that example that I made of planting trees, if you're planting trees and you're making a forest to offset some carbon, that forest, those trees have to live a certain amount of time, 30, 40, 50 years to absorb carbon every year, and therefore to offset the carbon that you've used. There have been some unfortunate examples in the past that some company bought some carbon offsets in some country and they planted the trees, but after 5 years, they chopped the trees and they sold the timber, essentially. So that was ineffective use of resources that you did in your project, and it did not end in any environmental impact at the end of the day. The other argument that people who oppose carbon offsets make is that it prevents innovation. So in terms of that American airline, the American airline, again, American Airlines, instead of going and buying carbon offsets, could spend that money in some research for combustion engines and also in some research for alternative fuels that are greener, right? People argue that that money is not spent because American Airlines is spending money in planting trees. I personally think carbon offsets can be effective, right? But you really need to be very conscious, very smart about where you are getting it from and how you're using it, right? You're not just using it to justify you. I think it has to be used as a last resort, right? You have exhausted any option that has been available to you. You still want to go carbon neutral and you can't because the way a concrete structure works today is not carbon neutral. So you have the option of buying carbon offsets. Now let's go to some material specific decisions. And first example is that you have a steel structure, right? What you can do in a steel structure to reduce the carbon, embodied carbon, is one is quantity optimization. And by quantity optimization, I mean, obviously you have to be in your design as lean as possible. But also when you have option in the case of a beam and you're choosing between different W sections, you definitely want to go with the W section that results in less weight per linear foot. And that again might have an implication that the height of your section might increase. So it needs more coordination with the architecture, vertical spacing, interior design, and a lot of other decisions that have to come in play, essentially. And then you can play a little bit to some degree with the sourcing. And by sourcing, I don't think if you're living in Florida, you can order some material from California. That doesn't happen. But you can specify that you want recycled steel that is produced with electric furnace to be used in this project. And that is usually doable because there are mills available almost in everywhere in the country that can deliver that material to you. And eventually, because steel is very dependent on the electricity and energy grid, at least in the United States, there are some good news that the energy grid itself is becoming cleaner every day. So this is from year 2000. If you compare it to today, we started with 1,400 pounds of CO2 per every megawatt hour of electricity that was produced. This is national average. And today we are almost half of that, at 800 pounds of CO2. And that directly affects how much carbon intensive your steel is, right? Everywhere in the country. So those are good news. Then material specific decisions, let's talk about concrete. And here, whatever I really know, I learned it from Dr. Suraneni here, but I'll venture to explain a little bit of it to you. If you remember from when we were talking about concrete, cement, and specifically baking the limestone into the kiln was where majority of the carbon came from in the concrete, right? So the first thought that comes to mind, let's get rid of that cement as much as we can. One way is to use blended cements. Blended cement is very similar to ordinary Portland cement. The only difference is that some of the one portion of that limestone essentially is not cooked, is grinded and is added later on. So it less energy intensive. It can be 10 to 15% less carbon intensive if you compare it to Portland cement, ordinary Portland cement. Then you have cement replacement option, and now we are talking about fly ash and slag and other, ground glass and other supplementary cementitious materials, as they call it. There is a great option, but it has some complications when it comes to real design of a project. So great option in sense that if you assume that fly ash and slag are almost zero carbon intensive compared to cement, if you're replacing 50% of your cement with fly ash, you're reducing 50% of the embodied carbon of concrete. That is fantastic, and I think it can be used in many elements in a structure, including a foundation. Why? Because when you're adding fly ash and slag, chances are that you cannot gain early strength, 3-day, 6-day, 7-day strength in your concrete, and you have to wait a little bit longer. It's more challenging to gain early strength with high percentage of replacement of SCMs. So it can be used up to, I think, 75% in an element like a foundation. Why? Because the foundation, you design it, you pour it today, that foundation is not going to see its design load until the structure is topped off, essentially, right? So, and that might take 8 months to 1 year. So you can specify a concrete that gains a strength in 120 days, in 90 days, and there's no problem with that. Then there are some elements, including the post-tension slabs, that the way it works is that I have a picture right here on the screen. You have the forms, you have all the tendons and cables, you pour the concrete, then usually the way it works today, after a day or two, you need to gain 3,000 PSI strength in the concrete to be able to pull the cables. And you want to pull the cables as early as possible because that affects the project schedule. You just want to pull all the shoring from underneath one slab and go to the next slab and continue going all the way up. So if you are shooting for 3,000 PSI in 12 hours or 24 hours, which is very common when you're pouring PT slabs, it is challenging to replace 50% of cement with fly ash. It's doable, but then instead of having a 6,000 PSI concrete, you probably have to specify 8,000 or 9,000 PSI concrete to gain an early strength that works for you. So it's offsetting a little bit of that reduction that you have been making in replacement, in cement replacement. Then you have the option to use recycled aggregates in concrete. And I think that is very great. It might not affect the carbon intensity that much, but I think if you think about sustainability as a bigger umbrella, it makes a big effect and big notch. However, again, you need to be a little bit careful because when you're using recycled aggregates, the quality control of the material is not the same as if you were using brand new crushed stone, right? So it can affect some stuff, including water absorption in the concrete, and then eventually that it shows itself into shrinkage. And if you are pouring a flat slab in Florida in summer, shrinkage is not your friend. So you don't want to play with something that, exacerbates that shrinkage problem that you had. So it can be done. I think it has to be controlled to a certain amount based on what I knew today. And it has to be studied very well in trial mixes that you do before. Then for RC or reinforced concrete slabs, you have a good option of using void formers, and they're becoming very common in Northeast, in New York projects. They are almost everywhere these days. What they are, as I'm showing it in the top picture here, they're basically bubbles inside your RC slabs. And what they do is that they reduce the amount of concrete, overall amount of concrete that you're using. However, your slab still has good functionality and performance for serviceability and also for strength. So they are a very good option. They cannot be used in post-tension slabs, which is very common in Florida, in Miami in specific. Almost every project, hardest project that we do, they have PT slabs. And the reason is that they need to save on the vertical spacing of the floors. But I do want to talk about PT slabs. I know that I talk about PT slabs and how carbon intensive the concrete of PT slab tends to be, because you need some early strength. But on the other hand, a PT slab is much thinner if you compare it to an RC slab. So an RC slab that is usually you need to design it for 12 to 14 inches. If you have a 30 by 30 bay, you can reduce it to 7.5, or 8 inch of concrete. So you are basically slashing the amount of concrete that is used in the slab by 40%. And that is a big saving. On the other hand, is a little bit more carbon intensive. And then you have the option to use different technologies that are being commercially available every day. Examples are carbon cure, that they inject some carbon dioxide right into the concrete. There is Blue Planet, Solidia. Some of them, they use solidified aggregates instead of crushed stone aggregates. Some of them are using in technologies just to make more efficient kilns for cooking the limestone. There are different technologies. I can't go into every single one of them. Based on my experience, they can push the limit a little bit, around 2 to 5%, not more. They're not as effective as using blended cements or cement replacement, but that's been my experience. Maybe there is some technology out there that I'm not aware. I'll be very happy to hear about it. And then the last but not least, of material specific decisions you can make to reduce embodied carbon. Let's talk about wood. So we said that you need proper forest management and sustainable forestry to begin with. That's a must. We are not even without talking about carbon intensity. And for that, there are 2 certification standards for any lumber that is in the market. Either they are certified by Forest Stewardship Council, FSC, which is a certificate done by environmentalists or created by environmentalists, or they're certified by Sustainable Forestry Initiative, SFI, which is a certificate done by the industry. Obviously, you can guess that the first one, the FSC, is more stringent and more strict than SFI, because it's done by the environmentalists, but either of them really work good in our experience. When you adopted lumber that has one of these certificates and you dig a little bit deeper, mostly and almost all the wood that is available in the US market, it ensures automatically, it ensures that you are not taking your wood from a primary forest. It is a forest that has been basically created for harvestation, and they have a good rotation. So depending on the species of wood, the rotation can be 30-year, 40-year, 20-year, depends what you're using, right? And that rotation ensures that the soil is intact. That rotation ensures that the wood has enough time to absorb carbon dioxide during its life. It ensures also that you are not using a lot of chemicals to grow the trees and many other good things. But yeah, you just want to keep an eye on the items that they have in bullet point here. Make sure that they're not from a primary forest. Make sure that they have the longer rotation period, the better, because it gives more time for absorption. Make sure that they address other metrics, including using chemicals for the soil and whatnot. Make sure that they are local, because you're reducing the transportation cost of it. And if you can, specify wood that is air dried instead of kiln dried, because to dry it in kiln, you have to, again, consume some energy. It's not very energy intensive. A lot of them use either electricity or they use biomass or wood pulps that, from milling, the leftover from milling to burn and dry the wood. But if it's air dried, it's more essentially more sustainable, less carbon intensive. Now I want to go to some of the market trends and what is happening in construction industry. So there are three big initiatives. There are a lot of them, but the three biggest ones that affect the construction industry is AIA 2030, that is for the architects to reduce embodied carbon and go carbon neutral by 2030. We have MEP 2040, which is committing to net zero for mechanical, electrical, and plumbing engineers, and they committed by the year 2040. And then eventually we have us, the structural engineer, which we committed to net zero by 2050. There's a long way to go, but also structurally, that is the hardest part to do because the most of the material that is used in a building is the structure, really. So it takes a lot of, I think we need a lot of technology to come in before we can go to net zero. We commit to net zero, but we shall see how it goes. And then there are some good green building certifications, including BREEAM, LEED is the most famous probably, and then carbon certification. These are the three most famous. There is a lot more. There is Florida Green Building Association that gives some certificates. And all of these, the latest versions, they have some incentives for reducing embodied carbon. And also they have some incentive for just running a life cycle analysis in a building. Which is really good because a lot of buildings that we do, they target to meet one of these certificates. And in turn, it incentivizes them to go towards reducing the carbon emissions. Let's talk a little bit about embodied carbon policies because we were talking about, again, incentives, right? There are some states like California and Colorado that they have a Buy Clean Act that requires two things. First, that any material that you're using in a building, you have to disclose the EPDs for the material used, right? If it's concrete, you're submitting the EPD for the concrete. If it's steel, the same way. And the second is that there are some set performance for the cap limit of GWP or global warming potential, or the amount of CO2 released into atmosphere per pound of material that you're using. So if you're using rebar or you're using hot rolled steel shapes, there is a cap for it, that you cannot exceed that cap. And that in turn enforces a lot of projects to essentially go less carbon intensive. I think there are a lot of cities that the city as a jurisdiction adopted to have a lot of initiatives. I know Portland, Oregon, Seattle, and many other cities, they have requirements for city projects to have, again, a limit on the amount of GWP that they're using per material. They require EPDs and many more, but it's not shown in this map. And then eventually, let's talk about the big players in industry and how they're going about carbon neutrality. Apple, Amazon, Facebook, Microsoft, all of them, they have a pledge that by 2030 or 2040, they go carbon neutral. And that is important because Apple and Amazon and Microsoft and a lot of these, even Meta, they have warehouses and they are creating a lot of, they are involved in construction. And when they commit to go carbon neutral by 2030, and they have already started, they are forcing the rest of the construction industry, in my opinion, to follow suit. And also they are breaking grounds in a lot of R&D, if you want to call it, the first time for a building to go carbon neutral, right? In a lot of projects that they do, granted that a lot of it is warehouses or maybe Apple stores for in case of Apple. But again, it is, I think, great pilot projects in this new era of reduction. And I think a lot of other developers and contractors and structural engineers are just going to get pulled into this atmosphere that Apple and Amazon and Microsoft are creating. And it's a good thing. That was my talk. I would be happy to hear your comments, questions and answers. And again, as someone who's practicing this, I know a lot of you are experts in materials. I would love to know your opinion and your suggestions, comments on a lot of what I said.